So I would also like to extend my thanks for you all sticking around today. And I would also like to thank the organizers. I was a latecomer to the session. I submitted a paper in hopes that there was some availability, and there was. So thank you to the organizers, and thank you to all of you that are hanging around for my talk. So yeah, I'm from Penn State University's Brandywine campus. It's Philadelphia adjacent. It's a very nice area, very small, quiet campus. So this main idea of this slide is just Michael Ferrara pointed out how his degree sequences were from largest to smallest. Mine are smallest to largest. So these are going to be non-decreasing sequences just because it works for the results to come. So also the terminology graphical when given a finite sequence of non-negative integers means that there is a graph that has that sequence as its degree sequence, and we would call such a graph a realization of that particular graphical sequence. So what Michael Ferrara spoke of is potentially having a property, meaning that there was at least one realization. Here I'm talking about the forcibly end of the spectrum, where we want to say that there's a graph property and we want to look to see if every realization possesses that property. That's forcibly P having that property for every realization. And I want to talk about theorems that look at a graphical sequence, apply some conditions, and if those conditions are met, then every realization will have that property. So it would be called, in this case, a forcibly P theorem, or just a P theorem. So a P theorem is a set of conditions. You check the graphical sequence against those conditions. If they're met, every realization has the property. So these might be just necessary conditions, not necessarily, most instances I would say they're sufficient conditions, but not necessary conditions. So as far as demonstrating something that in this case is potentially connected, it has a connected realization, but it's not forcibly connected because it also has disconnected realizations. So I want to preface the result I'm going to speak about by looking at a classical result by Bondi, which indicates here that if the conditions are met by the graphical sequence, so this set of implications, if they are met, then every realization is S-connected. Okay, so this is a forcibly S-connected theory. And this is what the collection of conditions would look like if you had 8 vertices and you wanted it to be 3 connected, or every realization to be 3 connected. So there are 3 of these implications to check if they're all met. So this puts out a sufficient condition. It's not actually a necessary condition. Okay? So some things that this particular theorem has is this property of what we're going to call monotonicity. Now monotonicity, we're going to define it using a notion of majorization. Now this notion of majorization may be different from one that you're familiar with, but for us, majorization is you have 2 graphical sequences of the same length. One majorizes the other if it's term by term greater than or equal to the other. And we just use a greater than or equal to symbol to signify here pi prime majorizes pi. So here's an example of pi prime majorizes pi, in that it's term by term greater than or equal to. Okay, so that's the concept of majorization here. A P theorem is monotone increasing, or for us we're just going to say monotone, if whenever it declares a graphical sequence forcibly P, it will also declare every majorizing sequence forcibly P. So it's monotone in that sense that if it declares forcibly P, then every bigger sequence in some sense will also be declared forcibly P. So in that case, Bondi's theorem is monotone. If you have a graphical sequence that meets these conditions, then any majorizing sequence will also meet those conditions by construction, just how those conditions are laid out. Okay? So optimality, well, optimality is when you have a P theorem, and not only is it sufficient, but it's also necessary. Okay, so in other words, if your graphical sequence fails the conditions, then it's not forcibly P. Now, many of these known monotone P theorems are not optimal. So we have that if it meets the conditions, then it's forcibly P, but if it fails the conditions, well, we don't know. It might be forcibly P, it might not. Okay? So Bondi's theorem is not optimal because it is sufficient but not necessary. Right? Here's an example of how Bondi's theorem is not optimal because we have here this graphical sequence. It fails the condition for s equal to 2. If you put it into Bondi's theorem, we get this implication, which fails, but it only has this realization C5, which is 2 connected. So even though this is, in fact, forcibly 2 connected, Bondi's theorem didn't classify it as such. Okay? So our goal then is to identify, in some sense, a best possible P theorem, in that it's sufficient, not necessary, but it's going to do something special. So here, we want to make sure that, let's say out of all of the known constructions for P theorems, so we have these P theorems that exist. For Hamiltonicity, there are a number of monotone degree sequence theorems that exist, but some are in some sense stronger than others. And the idea here of stronger, or best as we're going to say, is that it casts the widest net of all the P theorems for that property. So T prime is what I would call the best one, because if you had any other monotone P theorem, if you look at all of the graphical sequences that the other theorem T classifies as forcibly P, T prime will also classify those as forcibly P and possibly more. Okay, so it casts the widest net of all possible P theorems for that property P. So we may be thinking, well, why would you want to look at the sets of graphical sequences that this one classifies as forcibly P and this one, and then look for the one that classifies all of the others that are already classified and more? Well, we're going to call the one that is best the best monotone P theorem. And it turns out that you don't need to actually look at all of the classified graphical sequences for all of the P theorems and then compare. What you need is a concept of weak optimality. If your theorem has this property of weak optimality, then it will be the best monotone theorem for that property. And weak optimality is, let's say you have a graphical sequence and it fails the conditions. So now that's inconclusive, but you're guaranteed that there's a majorizing sequence that is not forcibly P. Okay? That's the weak optimality, and that would imply the best monotone. And in fact, yours would catch the most graphical sequences that are forcibly P out of all the monotone P theorems. So that's pretty significant to know. Like Bondi's theorem is weakly optimal. It's possible to prove that if a graphical sequence fails, there is a majorizing sequence. Now, if the graphical sequence has a realization without the property P, then that's the majorizing sequence without the property P. You wouldn't have to find a bigger one, but sometimes you have to find a bigger one that is not forcibly P, and thus you have the weak optimality. So the reason why I'm skipping ahead is I just wanted to summarize what this slide said. So this is generating a best monotone theorem. So the idea here is you have a property for which you want to create a best monotone P theorem. So you want to lay out degree conditions that are sufficient and also provide a weakly optimal P theorem. So what ends up happening is if you would like to find the conditions that produce weak optimality, you look at finding, if possible, the edge maximal graphs that do not have the property P. In other words, adding a single edge anywhere, the graph will now have the property P. So you look for all of those graphs that have as many edges as possible without having the property you want. Then you look at the degree sequences, and you look at the maximal elements of that poset imposed on the graphical sequences without the property of being forcibly P. And you want the maximal elements, so you want the ones that are biggest and don't majorize each other. Okay? You want the maximal elements of the non-forcibly P graphical sequences, and the majorization is the partial ordering. Okay? But to do that, you're usually looking for the edge maximal graphs that are not the ones with the property you're looking for, and then you construct their degree sequences, look for the ones that don't majorize one another, and create conditions that those degree sequences fail. So, in the traditional sense, we usually look for, like, S-connected means that the connectivity is at least S. So K-component order S edge connected is when that connectivity is at least S. So I wanted to look for monotone theorems where if the conditions are met, then every realization will be K-component order S edge connected. This is a simple monotone theorem. It's a single implication. If it's met by the degree sequence or graphical sequence, then every realization will be K-component order S edge connected. It's not best monotone, however. Okay? It's not weakly optimal. So I started looking for which one is best monotone, which one does guarantee the weak optimality. So I started with, S equal to 1. So the sinks are these maximal graphical sequences without the property, so they don't majorize each other. And they come from degree sequences of edge maximal graphs without the property. So if S equals 1, so let's say the lower bound you want is 1. Removing one edge, and you'll break up the graph into components, all of order at most K minus 1. So if you want the lower bound to not be 1, that means it's 0. So you want the edge maximal graphs so that removing no edges leaves you with components all of order at most K minus 1. So how do you do that? You just have a bunch of complete graphs because you want them to be edge maximal. So you have all these components by partitioning the number of vertices. But you need to partition the number of vertices in such a way that each part is at most K minus 1. Also, the two smallest parts, the sum has to be greater than K minus 1. Because if the two smallest parts had a sum of vertices that was K minus 1 or less, you could just add all edges between them and get a component of order at most K minus 1. So you need the sum of the orders of the smallest two components to be greater than K minus 1. And it turns out to do that, you just need the partitions of the number of vertices so that every part is at most K minus 1 and you have the fewest number of parts possible. That's this omega. That will always guarantee that the sum of the two smallest components, if you add up their vertices, will be K or more. Okay? So these will be edge maximal, not K component order 1 edge connected. They'll be 0 edge connected. So if you block those graphs with degree conditions, then you get the best monotone theorem. But it's not a theorem that covers all K in one fell swoop. You have to look at all the partitions of the integers. And the way I state the theorem is with respect to the remainder mod K minus 1. That's what this I is. So n is I mod 3 because here I'm doing an example where K is 4. So down below, these are the edge maximal graphs whose degree sequences we have to block, the ones that have to fail the conditions. So that's where the conditions come from. So the first condition, when I equals 0, blocks that graph. The second condition, the or is because you're blocking 2 graphs. And then the third condition blocks 1 graph. Okay, so for k equal to 5, you would have a different set of conditions to block different graphs depending on the partitions and so on. So then the natural ordering would be, okay, so that's how you would construct best monotone theorems for S, in other words, a lower bound of 1. What if you want a lower bound of 2? So you have to remove 2 edges before you have components all of order at most k minus 1. So if you want the edge maximal graphs that you have to remove 1, not 2, because you want to have these graphs be not 2 edge connected. So 1 below that is 1 edge connected. So you want to remove 1 edge to leave components all of order at most k minus 1. So those would be the edge maximal graphs, where you add 1 edge to those graphs that are just separate connected graphs, or the separate complete graphs from here. Just add 1 edge between 2 of these components. Then you get edge maximal 1 edge connected, or k component order 1 edge connected. But there are different ways you can add those edges. You can add the edges between various pairs of components just to produce unique results. So you produce all of those degree sequences, and it turns out that all of them are sinks. All of them are the graphical sequences you want to block, except for when all of these are true, except for this one special instance. K is at least 4, n has a remainder of 1 mod k minus 1. The smallest component in this collection of complete graphs is a k2, and the edge added to h does not have both endpoints in copies of k sub k minus 1, the 2 largest. So as long as you're not in this special case, you've got to sink, make the conditions that block it, put those into your best monotone theorem. So here are the sinks or the realizations of the sinks. These are the edge maximal 4 component order 1 edge connected graphs. So they're not 2 edge connected, they're 1 edge connected. So this notation with a line and an e over it means add 1 edge between those 2 components. So when I equals 0, there's only 1 possible configuration. You add an edge between 2 k3s. When I equals 1, we had a 1 followed by k3s. So what could you do? You could add an edge between 2 k3s or a 1 and a k3. Then there was an instance where there were the 2 k2s and the rest were k3s. Now, in order to get a sink and a maximal element of the graphical sequences, you would only add an edge between the 2 k3s, none involving the k2s, according to the theorem. So I indicated that here. That's a special instance when k is 4 or more, and the remainder is 1. You don't include any of the degree sequences that come from adding an edge. If the smallest component is a k2, you have to add the edge between 2 k sub k minus 1s in order to get a sink. That's the only way to do it. So these are the graphical, sequence conditions or the degree conditions that block those. So you get 4 component order 2 edge connected, and those are the conditions. If you wanted 5 component order 2 edge connected, and you look at all of those degree sequences that have to be blocked, these are the conditions for the various remainders. And then this was my undergraduate research student for spring 2023, Kenneth Wang. He was a computer science major. And I actually had him write a program that found all of when you had the edge added in, find all the degree sequences and find the ones that were not maximal, ones that got majorized by something else. So that's how the theorem came to be. It was that his program confirmed the theorem. So I had the theorem, he ran a program where the only exceptions that came out of his program, he would input n, he would input k, and then the only times we got any exceptions, it was in these instances. So as part of his final assignment, I was like, well, run your program and write down all the conditions for k equal to 6 to create the best monotone theorem. I know it's not very bright, so it's hard to see, but there are very many. And then the last slide was, well, look at how the conditions increase, not only with k, but this is just for a lower bound of 2, so s is 2. When s is 3, it's going to become even more, because what's happening is, when you want a lower bound of 3, you need to find all of the edge maximal graphs where you add in 2 edges. So that way you have to remove them to get those separate components. So when you add in 2 edges, there are more ways of how you can distribute those 2 edges to get unique degree sequences. And if you have, like, for example, you want a lower bound of 10, so you want 10 edge connected, so then you need to look for all the graphs that are 9 edge connected, edge maximal, and block those degree sequences. But there are a lot of different ways to distribute those 9 edges and produce unique degree sequences. So in general, if you have a k value and you have s greater than or equal to 3, and then n is large enough, then there are p of s minus 1 sinks. So the number of degree sequences that we have to block for our best monotone theorem to work, it actually is a partition function evaluated at s minus 1, so that's not polynomial. So you would have these number of conditions required will grow super polynomially as you increase the lower bound on your edge connectivity. So it gets unwieldy at that point. So here I wanted to mention that this is the title of the paper that I've uploaded to the archive, and it's also been submitted for publication in an open access journal. But the preprint is available on archive. So thank you.
Questions, comments? Okay, so let's send them out again.